In our previous bit of learning, we learnt that chemical reactions either release energy or absorb energy. And we classify these as being, if it releases energy, exothermic, and if it absorbs energy, endothermic. We also learnt that a certain amount of energy is required to start any chemical reaction. We call this activation energy, or EA. The reason that this works is because chemical bonds contain energy within them, and this is called bond enthalpy, and we're going to learn about that shortly. Well, the amount of energy required to break these is. So there's quite a simple rule, and that is that to break a bond requires energy. Bonds form because they are a more stable arrangement of the particles than them being atoms, for example. So to break a bond requires energy because you're trying to get these particles into a less stable arrangement. So it's endothermic. When a chemical reaction occurs, then new chemical bonds form, and bond formation releases some energy because the particles have got less energy when they have a bond between them. They're more stable. So this is an exothermic process, the formation of bonds. Those bonds could be ionic in an ionic compound, so the bonds between the ions. They could be metallic, so they're the attraction between the cations and the sea of valence electrons. They could be covalent, so between atoms in something like CO2, or between the atoms in a macromolecule such as diamond, so your 3D networks. And they can be intermolecular, so between molecules, so between CO2 particles. So to give you a quick idea of that, if we have CO2, I'll just do a simplified diagram, and we have a couple of CO2 particles next to each other. The covalent bonds are the ones between the carbon and the oxygen. And the intermolecular are the ones between the two carbon dioxide molecules. And they both are part of the enthalpy or energy of, say, for example, dry ice, which is solid carbon dioxide. So if bond breaking requires energy, we can apply that to our changes of state. It takes energy to go from solid to liquid. We know that because we heat things up to melt them. So that must be an endothermic process. We can also experience that as feeling cold. If you put ice in your hand and let it melt, it absorbs that heat energy out of your body to break those bonds, and it ends up being liquid water. By the same idea, it takes energy to go from liquid to gas. Again, we can think about that with water. We know that if we want to boil water in a jug or on the stove, we have to put energy into that. Electrical energy gets turned into heat energy, which then boils the water. So we know that must be an endothermic reaction. Solid straight to gas, only some substances do that. For example, iodine, and it's called sublimation. It's also an endothermic process. Conversely, going the other way, so reverse sublimation, condensation, freezing or solidification are all exothermic. While the product of those may be colder, the process itself is releasing heat energy or releasing energy. Don't do this at home, but if you get steam on you, it releases so much heat energy into you to try to become liquid again that you get a burn. That energy goes into your cells, into your skin, and you get burnt. Going from liquid to solid, so think about the freezer. The freezer removes that energy. That's what the coolant does, is it removes heat energy from liquid so that it can turn into a solid. So those ones are quite, I think, easy to understand. The particles are getting closer together. It must be that they are making more chemical bonds. Bond formation is exothermic, so the blue lines here must be exothermic. I want to melt something or boil something, I have to put energy into it. They must be endothermic. But what does that look like in a chemical reaction? Well, in an exothermic reaction, we've got to put a little bit more energy in to break the chemical bonds of the reactants. So we've got our reactants here and our products here. We need to put a little bit more energy in. So that activation energy is the energy required to break those bonds. Then when they have had the bonds broken, they then create a whole lot of new chemical bonds. And the chemical bonds here are a lot more stable. They have a lower enthalpy. So the rest of that energy gets given off as heat, maybe light as well. So this activation energy is the energy required to break the bonds. Then when all these new bonds get made to make the products, they're at a lower energy, so that's why heat is given off, and this is our typical exothermic reaction. Likewise, if we go from reactant to product in an endothermic, we see that we need to add a lot of energy to break the bonds. This activation energy again. Then, because the products have got a higher enthalpy or energy than the reactants, then it doesn't drop quite as far, but this bit here, this downward slope, is bond formation. So the two downward slopes are bond formation. The two upward bits are bonds breaking. So now we're starting to understand our graphs a little bit more and see that we can apply this idea of making and breaking bonds to our graph, but also to our old established knowledge of melting, boiling, freezing, and all those other physical processes that we now can start to consider to be a chemical change as well,